So why is the night sky not as bright as the surface of the sun if space is full of stars? In an eternal, infinite universe, every direction should eventually hit a stellar surface, so the whole sky should blaze like daylight. Yet, a moonless desert night is dark enough that you see black gaps between constellations, and the Milky Way looks like a faint chalk smear. This mismatch is called Olbers' paradox, and it forces us to be precise about what we mean by brightness. Not the brightness of a star, but the brightness of a small patch of sky, the amount of light energy reaching your eye from a fixed apparent area. If we can track what controls that sky brightness, distance, the number of stars, and how light changes on its way to us, we can see which hidden assumption makes the daylight-night argument fail. In a perfectly static universe that lasts forever, darkness would be impossible. Picture thin spherical shells centered on Earth. A shell twice as far away has stars that are 4 times dimmer because light spreads over 4 times the area, but that shell also contains roughly 4 times more stars if the density is uniform. Those two effects cancel, so each ever farther shell contributes about the same sky brightness, and an infinite stack of shells would build a sky as bright as a stellar surface. Even interstellar dust cannot keep it dark, because dust that absorbs starlight heats up and must radiate that energy back out until it glows. So, the real universe must violate at least one ingredient of this setup: uniformity, eternity, or stasis, and that is exactly what we need to identify to explain the dark night. Which assumption breaks first once you remember that light has a finite speed? Light from the sun takes 8 minutes to reach Earth, and light from the Andromeda Galaxy takes about 2.5 million years, so looking far away is literally looking back in time. If the universe has a finite age, observationally supported by the Big Bang model and measurements of cosmic expansion, then there's an observable universe, the region from which light has had enough time to arrive since the beginning. That cuts off the infinite stack of shells, and it also matters that the early universe contained no stars for hundreds of millions of years, because gas first had to clump under gravity and ignite nuclear fusion. Finite light travel time therefore removes most of the hypothetical distant starlight, but it still leaves room for another effect to keep the visible sky as dark as it is. Even the starlight that does reach us is weakened by the expansion of space itself. Cosmic expansion is observationally confirmed by galaxy redshifts. As space stretches, the wavelength of traveling light is stretched with it, and that stretch is called redshift. A stretched wavelength means each photon carries less energy, and the same stretching also spreads the photons out in time, so the arrival rate drops. Distant galaxies end up dimmer than you would expect from distance alone. This is why a galaxy that emitted energetic blue or ultraviolet light can be received on Earth as invisible infrared, even if no dust blocked it. Expansion, acting together with the universe's finite age, turns the naive every direction ends on a star picture into a universe where much of the potential light is shifted and diluted before it can brighten the night. If expansion stretches light so photons arrive with less energy, why isn't the sky perfectly black in all wavelengths? Radio telescopes and microwave antennas see a nearly uniform glow called the cosmic microwave background, and it is measured, not inferred. It comes from a time when the universe was a hot, dense plasma, electrons and atomic nuclei constantly scattering photons, until cooling allowed electrons to bind to nuclei in a process called recombination, letting light travel freely. As space expanded, those photons were redshifted from the bright heat of a few thousand degrees to today's microwave temperature of about 2.7 degrees above absolute zero, which is why your eyes do not notice it. The surprise is that the universe is not truly dark. It is bright in microwaves, and the visible darkness is partly a consequence of how expansion moves the dominant cosmic glow out of our band of vision. The dark night sky is the signature of a universe with a beginning and an evolving scale, not an eternal static sea of stars. Because the universe has a finite age, there's not been enough time for starlight to arrive from arbitrarily far away, and early on there were no stars to send any. Because space expands, traveling light is redshifted, its wavelength stretched, so photons arrive with less energy and more spread out in time, pushing much of the cosmic glow out of the visible band. That is why the sky is not sun-bright. Most lines of sight end on empty space within our observable universe, while the microwave background is the leftover all-sky glow. Like if this was interesting, hit the subscribe for more and turn that notification bell on.